Good morning. Myself, Dr. A.N. Basugade, Professor and Head, Department of Statistics, Gopal Krishna Gokhale College, Kolhapur. Today we are dealing with unit number 1, that is multiple linear regression, and that to a part 4, in which we will study the multiple correlation. Already we have studied the multiple regression expressions and their properties also, or some variance of residual everything. Now the second part is multiple correlation. Now in this we will obtain the expression for multiple correlation coefficient in terms of simple correlation coefficient, and also we will study some of their properties. In a trivariate distribution there are three variables x1, x2 and x3. Then the multiple correlation coefficient of x1 on x2 and x3 can be defined as it is the correlation coefficient between x1, that is the first variable, and the joint effect of other two variables, that is x2 and x3 on it, that is on x1, and it is denoted by R1.23. In other words, we can define this multiple correlation coefficient of x1 on x2 and x3 as it is the simple correlation coefficient between x1 and its estimated value E1.23. Already we have studied that estimated value in multiple regression. So therefore the mathematical expression for the multiple correlation coefficient is, mathematical definition is, R1.23 is equal to covariance between x1 comma E1.23 divided by under root their variances, means variance of x1 and variance of E1.23. So we denote this expression by capital A. Now we will derive the formula for R1.23. Let n observations are observed from each of the x1, x2 and x3 which are measured from their means, so that the means will be 0. Now as we already know that the residual x1.23 is equal to x1 minus E1.23. So by simplifications we are getting E1.23 is equal to x1 minus x1.23, which is your first expression. Now we'll consider its mean of this E1.23. Mean means get the sum on both the sides and divide by n. So therefore summation of E1.23 divided by n, right hand side will be summation of x1 divided by n and summation of x1.23 divided by n. But already we have proved that the summation of x1 by n means x1 bar, first mean of first variable, that is also 0 we have proved. Similarly, mean of the residual, that is summation of x1.23 divided by n, will give you the x1.23 bar, and that is also we have proved 0, and therefore totally mean left hand side is mean of E1.23 is equal to 0. That is your second expression. Now we will obtain the variances. Variance of E1.23. What is the formula for variance? The variable minus its mean whole square. So using that formula, this is 1 upon n summation E1.23 minus its mean whole square. But already in expression 2 we have proved that this mean is equal to 0. Therefore we are remained with only this square. So this is the 1 upon n summation E1.23 square. Now E1.23 in expression 1 we have obtained, that we have substituted here, that is 1 upon n. E1.23 is this expression x1 minus x1.23 whole square. Square is there. Now I will expand this square and divide by n for each term. So this square means summation of x1 square divided by n, this x1.23 square divided by n, and product of these two with minus sign and 2 times summation x1 into x1.23 by n. Now this is as it is, first term is kept as is, the second term is kept as it is. The third term is, we know the property to if secondary subscripts are occur in secondary subscript of the other residual, then you can omit. So this secondary occurs in the secondary, then we can omit. So omitting this one, we are getting this one, this expression as x1 into x1.23. But reverse way we have applied, instead of omitting or deleting that after the dot numbers, we will add them. So using property to reverse way, we are getting this expression. So this what it gives, summation x1 dot 23 into x1 dot 23 means x1 dot 23 square. So this x1 dot 23 square, it is 2 times with minus sign, this is 1 times with minus sign, we are remain 1 times with minus sign. So this is 1 times with minus sign divided by n. So what it gives, this is summation x1 dot 23 minus its mean. If we write it as x1 dot 23 bar whole square, that x1 dot 23 bar is 0, and therefore we are getting only this one as the variance of residual. So therefore expression for variance of E1 dot 23 equal to sigma 1 square minus sigma 1 dot 23 square. That is the third expression. Now for we again obtain the expression for covariance also. Covariance between x1 and E1 dot 23. By the formula, E1 dot 23 will be replaced by this one, that is x1 minus x1 dot 23. But covariance means what? This suppose covariance of x and y, x comma y means what? X minus x bar, y minus y bar divided by n. So x minus x bar means x1 minus x1 bar into this complete expression minus its mean. Minus its mean is this one. But this x1 bar and x1 dot 23 bar, they are 0, therefore this bar term will vanish, and x1 bar is also 0, therefore this term also vanish. You are remained with 1 upon n, this x1 from first bracket, and from square bracket you are getting only first bracket as x1 minus x1 dot 23. So that is written in the next expression. Now I will multiply inside and divide by n. So this will give the x1 into x1 is x1 square divided by n, and x1 into x1 dot 23 divided by n. Now again we will use the property 2, and this will be x1 into instead of x1 I will write it as x1 dot 23. So this expression becomes x1 dot 23 square. So that is the next term, that is sigma 1. The first term is, this will give the sigma 1, and this will be by using property I have written this. So this will be x1 dot 23 square. So that will give again, because its mean is 0, therefore you are getting variance of residual as this, which will give the expression number 4 for covariance of x1 and E1 dot 23 as sigma 1 square minus sigma 1 dot 23 square as the expression 4 for covariance. Again the last term is variance of x1, that is sigma 1 square as we know. So that is the fifth one. Now we will use this expression number 3 as variance of E1 dot 23, expression 4 as covariance between x1 and E1 dot 23, and expression 5 for variance of x1 in expression A, where we have written the formula for R1 dot 23. So the numerator term will be from expression number 4, denominator under root sigma 1 square as the variance of x1 from expression 5, and the second term is from expression number 3, that is the variance of E1 dot 23. Now this numerator can be written as, instead of writing only this term, we will write it 2 times the root, under root sigma 1 dot sigma 1 square minus sigma 1 dot 23 square into under root the same expression 2 times. So this one time sigma root and this one root will get cancelled. You are remain numerator, you are remained with only this term under root, and denominator will be under root sigma 1 square. So that is written in the next step. Now I will divide the sigma 1 to both the terms separately. So this will give the 1, and this division will give the sigma 1 dot 23 square by sigma 1 square. That is the expression. Now I will square on both the sides. Therefore R1 dot 23 square will be without root this expression. So this is the expression. Now as we have already proved in the derivation of variance of residual, as sigma 1 dot 23 square can be written in terms of delta as, this is the expression, delta into sigma 1 square divided by delta 1 1. We have proved already in derivation of variance of residual, and this sigma 1 square remains as it is. Now this sigma 1 square and this sigma 1 square will get cancelled, you are remained with 1 minus delta upon delta 1 1 as your sixth expression. Now we know the delta matrix as 1 R12 R13, then R12 minus 1, and then R23, and the last row will be R13 R23 and 1. So using that one we'll obtain the delta and delta 1 1 as delta 1 1 is equal to 1 minus R23 square, and delta will give you this expression. Now we will substitute these delta and delta 1 1 values in this expression number 6. What we are getting? 1 minus, because it is 1 minus delta upon delta 1 1. So this is your delta and this is the delta 1 1 as 1 minus R23 square. Now if I take the minus sign inside, 1 minus 1 will vanish. This R12 will get the positive sign, R13 will get positive sign, R23 also get positive sign, and the other last term will get the negative sign. So this is therefore the expression for R1.23 square is equal to R12 square plus R13 square plus R23 square minus 2 times R12 R13 R23 divided by 1 minus R23 square. So which is the expression for multiple correlation coefficient in terms of total correlation, you can say, or in terms of simple correlation between 1 2 1 3 and 2 3. If you want only the R1.23, just you have to write this complete expression under root sign. Okay, so that will give the multiple regression, multiple correlation coefficient, capital R1.23. Now we'll go for the some of the properties, two to three properties of this multiple correlation coefficient. The first property is multiple correlation coefficient is always greater than or equal to 0. That we have to prove. Now as by definition in expression 1a, we have written it as the formula as R1.23 equal to covariance between x1 and e1.23 divided by variance of x1 and variance of e1.23. Now as we know that variances are always positive, therefore denominator value variance of x1, so that is always positive. Variance of e1.23, that is also a variance which is the estimated value variance, and therefore it is greater than or equal to 0. And the in covariance term we have got the covariance of x1 comma e1.23, the expression is sigma 1 square minus sigma 1.23, or just now we have proved, and that is also positive because the total variance is always greater than the variance of residual, that we have written here, and therefore that difference is again a positive. Now the numerator is positive, denominator is positive, and this second term of denominator is also positive. The whole thing become a greater than or equal to 0, which is the property. That is R1.23 is greater than or equal to 0, and hence the property. Now we'll go for the second property. The if observed value of x1 and its estimated value, as we know, e1.23, they are equal, then r1.23 is equal to 1. So we'll prove this property in reverse way. If r1.23 equal to 1, then estimated and actual values are same. Like that way we'll prove. Now consider this r1.23 equal to 1. We'll square both the sides. Again it will remain as 1. That is r1.23 square is equal to 1. But expression already we have proved it as expression for r1.23 square as 1 minus sigma 1.23 square by sigma 1 square, and that is equal to 1. Now I'll take 1 to the left hand side and this to the right hand side. So 1 minus 1 becomes 0. So this divided by sigma 1 square is equal to 0. What it gives? It gives sigma 1.23 equal to 0. What is sigma 1.23? Sigma 1.23 equal to summation 1 upon n summation x1.23 minus x1.23 whole square. But that x1.23 bar, that bar is equal to 0, and therefore it is only x1.23 square divided by n equal to 0. But already we have proved that mean of x1.23 is 0. Mean means what? Summation x1.23 by n, and therefore that is equal to 0. Now from 1 and 2 what we have seen? We have seen that the sum of the values as well as sum of the squares of values of x1 dot 2 3, they are giving the zero value, because if you take n to the right hand side, you are getting sum of the values and sum of squares of the values, the total will be equal to again 0. When it will happen? If and only if all the x1 dot 2 3 values are 0, then only it will occur. Thus from 1 and 2 we conclude that each of the residual must be equal to 0. That is x1 dot 2 3 is equal to each and every x1 dot 2 3 equal to 0. This, then only this can happen. And therefore we know the expression of x1 dot 2 3 as x1 minus e1 dot 2 3, and that is equal to 0. Therefore x1 equal to e1 dot 2 3. That is, the actual value must be equal to the estimated value. Then only we are getting the correlation, multiple correlation equal to 1. Thus observed value and its estimated value e1 dot 2 3 are equal. That is your second property. And the last property is property number 3. If R1 dot 2 3 equal to 0, then variance of residual is equal to the overall variance. Okay, so that we have to prove. Now consider R1 dot 2 3 equal to 0, thus its square is also 0. We know the expression for R1 dot 2 3 square as 1 minus sigma 1 dot 2 3 square by sigma 1 square, and that is equal to 0. Therefore, if I take 0 to the left hand side and this to the right hand side, so we are remained with this term, that is sigma 1 dot 2 3 square by sigma 1 square equal to 1. If we cross multiply, we are getting sigma 1 dot 2 3 equal to sigma 1 square. Means this is your variance of residual and this is your total variance, overall variance. So they are equal if R1 dot 2 3 equal to 0. So what it shows? This shows that if R1 dot 2 3 is equal to 0, then variance of residual is equal to the overall variance. Now from all these three properties, we can say that the multiple correlation coefficient lies between 0 and 1. That is, the range of multiple correlation coefficient